Good evening, everyone, and welcome. This is Professor Thayer with you here today to talk to you about working with cpptraj. This will be the first in a series about how to work with cpptraj. So today we will focus on an overview and working with cpptraj in the interactive mode. So I am sharing my screen with you here. I've set up a directory for me to work in, just as an overview. When you are using cpptraj, you do need to use it in the Unix environment, and you can install the Amber tools. This is a freely available package from ambermd.org that you can download and install on your machine. If you are an Amber user, you already would have Amber tools, but if you are not an Amber user and you simply want to use the Amber tools package, that is something that you can get for free. Now, what I am doing here is I'm working on an Ubuntu Linux machine, and let me just cd to my home directory so you just get a sense. So what I have done is I have actually made a directory called Amber Tutorials where I work on my tutorials and workshops, and then I have set up a directory to do these in. I have downloaded some sample trajectories. You can feel free to work along with your own trajectories, or you could go to ambermd.org and you could download the exact one which I am working with today. So I'm going to go ahead and cd into Amber tutorials, and I'm going to list, and the directory I have set up for us to work in today is this 41A cpptraj. You can go ahead and create your own directory using the mkdir command, just like I've typed here, and then you would give the name of the directory. So once you have your directory, you can use ls to view your directories, and then you can cd to change directories into your directory. Now you may also notice that sometimes the typing does not occur at a constant rate, and that's because we have the tab for autocomplete, so that is definitely your friend. So here you can see that what we are working with is two trajectories, which I have gotten from the Amber MD website, the tripzip2. This is the armtop file, and the .nc is going to be our compressed trajectory file. So what we're going to do then is we are going to test out our installations of Amber. So we can do echo $Amber home to see where our Amber home directory is located. We see that Amber is installed here, and that our Amber home directory is in home Kelly Amber 20 / Amber 20. So that's great news. That tells us that we have it and that this is its location. It also lets us know that we're working with the version of Amber 20, which was released in the year 2020. So in order to run cpptraj, you can use it from the command line, and you can also work with it in the scripting mode. So for today, we're going to work with it from the command line so you can get a sense of how you can do that and what the workflow is like. And then in the subsequent tutorials, we will take a look at, in fact, working with cpptraj using the input files. So for now, we are going to issue the command cpptraj, which will launch cpptraj, which we see right here. This tells us the date and also tells us about the memory. And we can also see the version of Amber tools, which we are running right now, which is version 19.10 in Amber 20, as we saw from our check of our Amber home variable. It's a good idea to have your Amber home set. If you're unfamiliar with that, you should set it up in your .bash RC. We have some tutorials on that if you need to work on setting up your environment variables. So the first thing we can do then is we can load our prompt.off file. Now our prompt.off file is going to provide the information in terms of the connectivity of the molecule, and it will also have all of the parameters in it. The parm part is the parameters, which you can set up using tleap. And the top is the topology part of the file that is going to explain how the atoms are connected together based on the building blocks you've supplied with it. So if you run your file through tleap, and you have set it up and completed and gotten a trajectory, you should surely by now already have some parm.top file available. So that will be the first thing that we will load in. So we do that with the parm command, and then we're going to issue the name of this file. And also notice that I can use tab to auto-complete the name. It will complete only as far as it is unique, so I had to do that twice. And then if I press enter, I should get a message that it is reading this in, which I do here. So the C and the non-bonded terms have not been set, so they have just been set to default values, which should be just fine. Now, when we're working in cpptraj, one of the things about how it works is that we can now have more than one parameter and topology file loaded in at once. So in fact, what ends up happening is it gets loaded into a stack. And so we might want to see which ones we have. And so we can use the list command in order to see which one is loaded so far. Now we're just going to work with one for the time being, but you could in fact load multiple parm.top files. And in fact, the CP part of the cpptraj refers to copy, which was made so that you could have multiple parm.top files loaded at the same time, meaning you can analyze more than one molecule, for example, to compare and contrast them, which is a very helpful thing to do. So we can do list, and we can do parm, and we should now see the parameter files which have been loaded in. So that's terrific. We now can see that we have correctly loaded in one of our parameter files, which is what we've done so far. Now, the other thing we might want to use is the parm info command. Now, the parm info is going to provide information about a particular parm.top file. So we're also going to tell it which one we want to look at. We can actually see from this line right here that we do have some information already. So the first thing we notice on this is the index number, which is 0. So as I mentioned, it will be loaded into a stack for the parm.top file. So this is the 0th item. It just means that the index begins at 0. This is something that Python also does. And the next one would be 1, and so on. So this gives us the name of the file. This tells us how many atoms are present in the system. Those are divided into 13 residues. There is no box information, and one molecule, of course, aside from the waters, has been provided. So now we can get some additional info by doing parm info, and then we need to say which one we wish to look at. So we will select the 0th item, which is the one we have just seen. And we can now see that we get some additional information. So this tells us, again, some of the information we have seen from before. We get the name of it. It takes this information and breaks this out for us a little bit more. It also tells us about the bonds, the angles, the dihedrals, and that there are no other, that there's no box information available for it. So that's okay. The box information is needed for the periodic boundary conditions in the MD simulation. So the box had been auto-detected. So that is okay. All right, the next thing we want to do now is we want to load in an actual trajectory. So at this point, there are in fact no coordinates. This is only just the parameters and how the molecule is hooked up together. So in order to do something interesting, we probably want to look at an actual molecule. So we're going to use the trajInt command, and the trajectory that we had is the tripzip2 one, which is this file right here. Notice I'm using the autocomplete because I have a terrible memory and don't always remember what I called things. So it's very helpful. Okay, so let's see, it says that we have a time variable defined but empty. So that's a bit unusual. I'm not exactly sure what that means. This is an older trajectory and I'm using a newer version of Amber, so that may have something to do with it. It's always a good idea to take note of the warnings, but if anything seriously goes wrong, cpptraj, as with many of the Amber suite of programs, is very good about stopping the execution of things that are going wrong. So I wouldn't be overly concerned just yet. All right, so now we have read that in, that's good. So we can also take a look at which items have been loaded by the traj-in. So we can do list traj in, and this is going to tell us about the traj-in stack. And again, we have the 0th item and we have one trajectory here, and it tells us that, and it is explaining to us the number of frames that are available. So we have a molecular dynamics simulation with 1,201 frames. So the next thing we may wish to do is actually do some activity. So let's say I wanted to measure the distance of something. Maybe I forgot how the distance function works. So I can use the help. So I'm going to do help distance. Okay, and now we see that this is very useful, that we in fact get this nice manual page about how to do this. It explains what all of the options available for it are going to be, and also tells us what it does, that it calculates the distance between some atoms in the masks. And so when we read this, basically we need to have some understanding of what the mask is. But if you have set up your trajectories prior, you've probably encountered the masks already. Basically, this is a selection of the atoms. We think of it as a mask because it hides some of the atoms and allows some atoms to come through like a sieve. And so what this is going to do is it's going to allow us to select the things that we wish to look at, and that in Amber is called the mask. It's pretty consistent between the MD through and cpptraj and tleap and all these things. There are things where you may need to supply a mask, and that's what we're talking about here. So now that we know that we can calculate the distance between some atoms, that's great. Maybe we want to find out some information about the residues, so we can do res info just like this. And this will now provide us the information about our molecule. So what we can see from this is that we in fact have 13 residues in our system. This is a protein. The residue numbers are listed out for us, and we can see the number of the first atom that's in each one. So this one runs from 1 to 13. That's a serine. And it also tells us how many atoms. I'm not sure what orange mean. This is basically an index for your residues. It's the same as the residue number. I think it's because it may renumber the residues for you in one of these indices. So it's telling you the original index, which for our case is the exact same thing. And this is the molecule number. And since there is only one protein in here, all of the residues have molecule number 1. So this is what we see here. We have these residues here, which you should recognize as the residues, the normal 20 amino acids, except this one, which is a capping agent, which we can see has been added to this system at the end. Okay, so now what we might want to do is we might want to get information about an atom. So we have res info, and we also have atom info. And so we're then going to specify number 13, which I'm going to do with the colon for the selection of the residue, and 13 to specify that's the one I want. So we mentioned this is the capping on the end, and you might want to know what it is. So we see that it's a nitrogen with 2 hydrogens, basically an amino group, and we can now see what the molecule type are, right? So it's nitrogen, hydrogen, hydrogen. It's called NHE. And we can see the partial atomic charges by the atoms, the mass, some electrostatic information, van der Waals, and some additional parameters that are being used by the force field to run the calculations on this. So you can get quite a lot of information about your system by using this interactively and asking questions just like this to figure out what in fact is in here. Now this can be quite useful, especially if your system gets renumbered and you want to make sure you've made the correct selections. This is a really good way to verify you've picked what you think you picked. All right, so now let us do an end-to-end distance. So I'm going to do distance. Now I'm going to use the end to end keyword here. And this stands for residue 1. End to end, actually, sorry, is not a keyword. I'm going to use, that's actually the name of the output. So I'm going to do residue 1 to residue 13, which we'll call end to end. So that's the variable names. You could call that anything, but obviously you want to pick something that is useful. So now we're going to use the out, that is a keyword, and that is going to now indicate we're going to make an output file, and we're going to do dist end to end .agr. Now the .agr is going to be significant in a moment. That is going to format the output so that we will be able to do some plotting, as we'll see in a moment. Okay, so here it is telling us we are using the center of mass points, and we are going to measure the distance between 1 to 13. So instead of picking some particular atom, it will take the center of mass of residue 1 and the center of mass of residue 13 and do a mass weighted center of mass distance calculation. So the next thing we might want to do is we might want to refresh our memory on what the actions are. So one interesting thing about how this actually works is it doesn't actually run all the calculations until you've loaded in all the commands, and then you must tell it to actually go and do the calculations. So in fact, it hasn't done anything other than store this information in terms of the commands that are going to run. And the same thing works when you're doing the script. This is a little bit different than what you may be accustomed to doing. And so we have this command, the list actions, to help us just assess what we have set up to do so far. So right now we've set up to calculate the end-to-end distance, which we can see right here. So now, as we've mentioned, we haven't actually done anything. So the next thing we need to do is, in fact, actually execute it, which we can do using the run command. And so now when we execute this, this is a really small one, so it executes pretty quickly. So we see that it's read in one trajectory. Let me just see if I can roll up here a little bit. Unfortunately, oh, a little bit. Okay, well, it's very slow. Okay, so here's where our processing began, where it says this run begin. And so here you see I type run, and it's repeating my commands here just like that. And it's saying that it has one input trajectory, which is good because that's what we told it to do. And this is the trajectory that it loaded in. And it says it's going to process 1,201 frames, which is great because that's how many we thought that it had from what we had seen before. Now we begin the trajectory processing. So it's going to now go through the things that are in the action stack. So it's going to set up for this parameter and topology file, which is good because that matches. And we said we want to calculate the distance, and we called it end to end. So it's repeating our command for us here. And here is our mask that we're going to do the residue 1 to 13 with the mass weighting. Now, this was super quick. And so this is calculated really fast and it's scrolled by us. But if you're working with a larger system instead of just this little test model system, you may in fact actually get stuck at this point. You'll watch these percents growing in, and it's telling you its progress on the calculation. Now it tells us it's read it in, and it tells us how long it took us to do it. Now we're going to get the output from the action. So this analysis all took 0 seconds. That's really fast. So here we have our data sets, the end-to-end, which was the name of our data set. And this tells us how much memory has been used for this. And here we have our output file. This is going to be for XM Grace to view this. And it tells us our runtime, initialization, trajectory processing, the action, post the analysis, the file writing, and other IO processes that may need to go on. So obviously this has occurred extremely quickly because we have a good processor on this machine. If you're working on another machine, it could potentially be a little bit slower, and especially if you're working on a larger system. But in general, this kind of process should be relatively quick, and you should be processing most trajectories within a couple of seconds on any kind of modern machine. And I'm not even putting this on the GPU. This is just running on the CPU on my Ubuntu system laptop. All right, so now that we have done that, what we want to look at next is maybe we want to actually graph this. So I should be able to do this using XM Grace. So I could try. Tab, AGR. I did not pick up that. Oh, because I guess I am doing this. Okay, and we do not have any data here. Okay, which is bad. I'm not entirely because it thinks that it cannot find this file. Let me try. I think I got the file name wrong. Into end. And this one is also empty. Okay, it's of course important to remember your file name. So unfortunately, I cannot see these. All right, I'm going to go ahead and move on, and we will revisit this momentarily. All right. I think the problem may be this. Let us just take a look at what we got here. Okay, so we did get this end-to-end.agr. So now let's do a little bit of troubleshooting. So I'm going to do ls minus l, and now it's telling me the length of all my files. So what I can see here is the permissions, who the owner and user is, the size of the files, and when it was made, and the name of the file. So clearly my end-to-end has been created here. So I'm not sure why I'm getting this error with the XM Grace. So I'm just to check this out, I can do head, and now I'm going to do dist, and so on. And so I see that I am getting some formatting for XM Grace, and I can also do tail, and I can also give the same name for my file, and I see that I do in fact have data here. So I'm not sure what the issue is, and I'm going to try running this from outside of cpptraj and see if we get, better luck. Yes. So it should be runnable from inside XM Grace, but for whatever reason, we're having issues. So I just ran that from the command line instead. And here we have our graph. These are not the most gorgeous graphs in all the world, but certainly it's great for checking your data and making sure that everything is working. So here we have it. This is your end-to-end distance from, from your trajectory analysis. All right, great. Well, that gives you the basic overview of how we could do a workflow working in cpptraj. It hopefully gave you a bit of a flavor for how we could work with some of the tools that are available there. It tells us a little bit about how it would work when you are doing something interactively, and you can see how useful that that has been. Now, I'm just going to also point out one final thing before we head out for today. So notice that after I have executed this, that one of the things that happens is that I in fact also get a cpptraj log file. So by default it's called cpptraj.log. So I can see that just by using my ls command, and I can again do ls-l to see the longer command for that to get the more information. And so what I can do is I can actually view my log file, and what it's going to do is it's going to in fact tell me all the things that we ran, and it will also and so this can be incredibly useful because you could use this as the basis for actually creating your input file if you wanted to in fact go ahead and script this. So the next time we meet, one of the things we'll be talking about is how to go from working interactively with cpptraj to instead using a script. The scripts can be quite helpful if you wish to repeat the calculation many times, share that calculation with another, use that information to log what work you've done. Interactive mode is helpful if you need to do things where you need immediate feedback. Maybe you're not sure which residues you want to connect up or work with or take the distance between. Maybe you are exploring your system. Maybe this is the first time you're working with that system. All of those are excellent reasons to use cpptraj in the interactive mode. But generally speaking, after we have done the interactive mode, we usually want to move into having the record in the script. And so it's very likely that you will, for your first trial and for debugging and troubleshooting and all those sorts of things, be working with cpptraj interactively like we have today. But it's very likely then in subsequent occasions that you would want to move towards having the cpptraj working off of a script. So next time we will see how we can do that. All right, I hope you have found this to be useful. I do encourage you to visit the ambermd.org and the Amber Hub web pages. They are excellent sources of information where you can learn more about how to work with the Amber tools and also interact with the authors of the program, see many more tutorials, and gain more in-depth information about how to work with these things. All right, well, thank you very much for joining us today. I hope you have enjoyed this, and we hope to see you next time to learn more about cpptraj. Thanks so much, and we'll see you later.